Hi there. We're going to take what we've learned about energy so far and make a little bridge between those concepts and math using energy transfers and bar graphs. So we'll show how we can represent the role of energy in physical change. At any time, if you need to pause the video to write down some notes or think about the process, please feel free to do so. A little review. A system is the part of the universe that we're studying at that time. The surroundings is literally everything else in the universe surrounding our system. A closed system has no interaction with its surroundings, usually it would have some sort of a lid or a cap. And open systems are those that can actually interact with their surroundings because they lack a lid or a cap. Remember our energy principles that we've talked about so far. Energy is a substance like quantity. It's not physical, it's just like data on a computer. Much like data on a computer, energy can be transferred from one system to another, and it always flows from high to low. But the energy itself does not change. How it's stored can change, though. We can use energy bar graphs to quantify changes in our energy storage. There are three energy transfer mechanisms. These came from the reading, so I'll go through these quickly. Working, or W, is energy that's transferred between interacting objects that exert forces on one another. These are macroscopic. This is something that's dealt with in physics. Heating, or Q, this is also known as heat, is when energy is transferred by collisions between particles, microscopic. Now this is what we're going to use this whole unit, so Q is important for us. Now, energy is always transferred from the hotter object to the colder one, much like we talked about if you're sitting on a cold metal bench. It feels cold to you because it is taking your hot heat. Review, objects don't store heat, but remember they can be heated. Now, radiating, or R, is energy being transferred by the absorption or emission of photons or particles of light. Think about how that feels when you're sitting in a car with the windows rolled up and it gets warmer inside the car. Now, the first law of thermodynamics can be shown with this equation, but don't stress. We're just taking a look at this idea that all of those little changes that happen in a system must add up to zero because the energy in a system cannot actually be created or destroyed, but it can be transferred in or out of the system, and it can be changed from one type of system or one type of energy to another by those three mechanisms. So thermal energy, or ETH, is the energy that's stored in moving particles. This is kinetic energy, something you are familiar with. As we know, the temperature of a system is directly proportional to its thermal energy and the motion of those particles. Phase energy, or EPH, is the energy that's stored in a system due to the arrangement of the particles, and they exert attractions on one another. These are known as intermolecular forces. As we add energy to a system, it helps those particles to overcome those intermolecular forces and increases the stored energy of that system. From lowest to highest EPH, solids have the least, gases have the most, but that's because gases are least attracted to each other, solids are the most attracted to each other. And then phase energy is the energy that's involved when phase changes occur. In other words, if a solid melts into a liquid. Now, chemical energy, or ECH, is the energy that's stored inside the chemical bonds, inside of molecules. This is really where the rearrangement of atoms forming new substances involves chemical energy. We're not going to get to this quite yet, but stay tuned, we'll bring this back. So, how do we show energy transfer? We're going to use energy bar charts, and we'll use energy accounts to show the amount of energy that's stored in the different ways inside of a system. And we'll walk through an example to learn how to construct energy bar charts or bar graphs. So here you're looking at one of those graphs. Sometimes it's known as an LOL bar graph because it looks like LOL. And here we see the system in the center, and then on the left you see energy before the transfer, and on the right is the energy after the transfer. So on the left, the initial conditions, we would have a certain amount of energy in each of those accounts, and then the final side, we would have another amount of energy in each of those accounts. So when we look at an example here, number one, a cup of hot coffee cools as it sits on the table. We first need to identify the system and its surroundings. our system is simply coffee. The surroundings is everything else, the air around the coffee cup, the table, and then we'll write the system in the circle, which is just coffee. Step 2, decide if chemical energy is involved. Well, here we're starting with coffee and ending with coffee. We're not going to let it sit around for weeks and grow mold, so our particles will not be arranged to form new substances. And again, we're ignoring it for this unit, but we'll come back to it later on. Step 3, assign values to EPH. This is where you're going to start. So we have to remember that solids have the least and gases have the most, and here you're going to want to jot down values that you need to know by memory. We're going to represent these phases by using these numbers of bars, and those little dashed lines is where you would mark each bar. Solids will get 1 bar, liquids get 2, now wait for it, gases get 4 bars. We never use 3 bars for phase energy. You can use it for thermal, but never for phase. And that's because gases are so not attracted to each other. They have a ton of phase energy. They are just jamming around. Then we're going to add those bars to the initial and final EPH in our bar graphs. So because we're starting with the liquid, we're going to put 2 bars of energy in the initial, and we're ending with liquid. So we'll end with 2 bars. So that was easy. Now we're going to choose our bars for thermal energy depending on the temperature. Now on the thermal energy, you really have some leeway here. In general, use more bars for high temperature and fewer bars for room temperature or cooler temperatures. You can choose a number of bars, just be consistent, clear, and logical. So here, I'm going to choose 4 bars to represent hot, and then 2 bars for room temperature, just because it's a really obvious change. You could have gone 3 to 2, that would have been fine. So that looks great. Now we need to show the energy transfer, because obviously we don't have the same amount of energy in our beginning and ending conditions, and we are breaking the first law of thermodynamics, and we're gonna go to the jail of the thermodynamics. No good. So our final system has 2 less bars of stored energy than the initial. 2 bars have left the system via heating. Remember, we're only using heating in this class, and we'll represent that with Q. So visually represent that with the number of bars that you have leaving in this case, and always, always, always show the Q, even though it's always going to be Q. The next step in this unit is we're going to do math involving Q, and so I want you to get in that habit. So make sure then that your math makes sense here. We have 6 bars in the beginning. We're losing 2 bars of energy to the surroundings, and so that's minus 2 bars, and we have 4 bars in the end. That math makes sense. We've not basically killed any energy. We've just given it to the universe. So all is well. Moving on. By the way, this is an exothermic process. The system releases energy to the surroundings. Energy is lost in this case. This would usually feel hot, because you're the surroundings. So think about if you're sitting on a hot metal bench on a summer day, or going down a hot metal slide on a summer day, and it feels really, really hot. That's because heat is moving from the hottest thing to the cooler thing, and you happen to be the cooler thing in this case. And think about for a moment, what would that look like on a line graph to start with more energy than you end up with? Moving on. Let's look at a second example. A tray of ice cubes is -8 degrees Celsius and is placed on the counter to become water at room temperature. How many steps is this? Would ice go directly to room temperature if it starts at -8 degrees Celsius? Think back to your icy hot lab. The answer is 2 steps, right? It's got to first warm up to, what temperature does water melt at? Hopefully you said 0 degrees Celsius. It's got to warm up to 0 degrees Celsius. Then it can melt finally to water. So remember, these happen separately. That's a really important concept. And we need to show this in 2 steps. First, draw yourself a heating and cooling curve before you do your bar graphs. The choice of bars for thermal energy is arbitrary. Just be consistent. Generally, we'll use 2 bars for room temperature and 1 bar for cold liquid, but you can modify that as needed. 8 degrees Celsius should be less than 1 bar. Technically, you can use 1 bar. I like to use half sometimes, but just try it again to be clear. So here we've got our heating curve. starting at negative 8 degrees Celsius, going up to 0. That's our temperature change. And then we're going to do our melting or phase change. Notice that's flat because there's no temperature change. So now let's do our bar graphs. We will represent these separately. Step 1, we're going to show this temperature change. So when we do that, we're going to show our thermal energy being quite low for our negative 8 degrees ice. And then you could just go up to 1 to 0 degrees. That's up to you. I wanted this to be really obvious, so I went up to 2. Now my phase, notice, does not change, right? Because this is a temperature change, not a phase change. Those never happen simultaneously, which is why we're graphing them separately as well. So our phase starts as a solid, ends as a solid, and those each get 1 bar. So here I've got 1.5 bars in my initial conditions, and I'm representing 3 bars in the end, which means I needed to gain 1.5 bars. And so I'm going to draw that by drawing 1.5 bars with a Q for heating. This is endothermic, by the way. We'll come back to that idea. Now we're going to represent step 2. This is 2 sets of graphs, but what you should know is because we are picking up at this exact little junction in our line graph, we can transfer our final bar graph from step 1 into the first step of step 2. So I'm going to redraw that, and so don't get freaked out by the fact that you have 2 bar graphs. You're just going to draw the second bar graph twice. So I'm starting now at the same amount of thermal energy as I had in the final conditions there, and I have 1 bar of phase energy because it's solid, and then all I'm representing in this is the phase change, and remember, liquids get 2 bars. And now I still have my ice tray. You could just say water because it's all the same substance. That's all good. And in this case, notice I have 3 bars in the beginning, 4 bars in the end, which means that I did gain 1 more bar of heating. And just because it's heating energy doesn't mean it's warming up, right? This is just a way that we can affect the particles' arrangement and motion. So we talked about this being endothermic. Remember, the endothermic is where the system would absorb energy from its surroundings and energy is gained. Now, in this case, it would actually feel cool to us because we are giving it our energy. In this case, think about if you are sitting on a cold metal bench on a cold day. It's going to feel really cold because you are giving the bench your heat from your tush. All right, last example, which is good because my dog is getting impatient. Example number 3, water vapor is at 108 degrees Celsius. It's cooling and condensing on a glass of lemonade. First, decide what's in the system. Think about that, everybody. Is it water or is it lemonade? Be careful. Decide whether chemical energy is involved. Never for this unit. Assign phase values, phase energy values. Think about what are we starting with and then what are we ending with. And then choose bars for thermal energy. What temperature does it start at and where does it end up? And then show your energy transfer. Those are our steps. So how many steps are in this scenario? Think about that for a moment. Maybe give this a shot before you continue on with the video. This is 2, like our last example. In this case, first it's going to have a temperature change and then a phase change. It's just the opposite of what we did in the previous problem where it had to warm up first. This time it's got to cool down. And again, these happen separately. So we have to show 2 steps. So here we're going to cool it down from 108 to what? At what temperature would water evaporate or condense? Hopefully you're thinking 100 degrees, which is correct. So step 1 will show the temperature change, and then step 2 will show the phase change. Step 1, we have water in our system. How many bars do phase energy for gases? Oh, and remember, there's no chemical energy here. We're going to have 4 bars for our phase energy for a gas. And that's going to remain 4 in our temperature change because there is no phase change here. Start really, really hot. I'm going to go 4 bars, and then I'm going to take it to 100 degrees, which is Honestly, still pretty hot. You could go to 3 bars. That's up to you. I went to 2, so it would be really obvious. Then I'm going to show my energy transfer. Because I have 8 bars and 6 bars, I need to lose 2 bars. And that is always through heating. So now I'm going to take that exact bar graph that I drew at the end of step 1, and I'm going to redraw it at the beginning of step 2. By the way, this is an exothermic process, right? Because we're losing energy. So I redraw that. My phase is still at 4 bars, but this time it's going to become a liquid, so hopefully you remember that's got to become 2 bars in the end. I'm going to start with my 2 bars that I decided on for the final of step 1. And in this case, I'm going to change my temperature. Hopefully you said no, because it's a phase change. It will still have 2 bars at the end. We have 6 bars in the beginning and 4 bars in the end. So what needs to happen? We're going to lose 2 bars, also through heating, and this is also exothermic. So hopefully that makes sense and that was helpful. Feel free to go back and review the video as needed.